David. You're gonna get one of these boards, and I'll ship 2 of the chips along with it. The board is pretty simple to set up. It has a power connector over here. I'm going to provide you a connector, and you already have push this in, and once it clicks, it's all set. Now this has 4 wires. One is for ground, and although it has 3 supply wires, 2 of them are actually 1.8 volts, so you can just combine these 2 and put it on 1.8 volts. And there's a marker here for 3.3. I would suggest you provide 3.3 volts, and whatever voltage you provide, your clock highest voltage needs to be that. If it is too lower than this, it may not work. If it is higher than this, it'll blow the chip on the board. And same here, 1.8 volts is the highest supply you can go for the Imager chip, so make sure you check the voltages before you power this thing on. When you're removing it, just be a little careful. Just prop open a little bit and then pull it, otherwise this thing will break. It's pretty flimsy. So once you provide the power, the 2 other connections you need to make is provide a clock in through this SMA connector here, and output, which again is a SMA connector, goes from here to the oscilloscope. The drawer card has a little white marker here, which needs to align with the white marker on the board here. Just have to be careful because this is not polarized, so you want to make sure all the pins are in line, because you can offset it by 1 row and it still fits, but it'll short the whole thing. So you want to make sure when you're changing it, you have all of them aligned and press it firmly so that it goes all the way down. It's very ESD sensitive, so make sure you have one of the ESD wrappers with you, or at least have a ground connection. When removing it, you have to be really careful. I'm going to provide you this tool extractor, so you just have to grab it, but you have to it's really tight, can't force it, so you nudge one side slightly and just kind of nudge it open and bring it out. The board is pretty simple to operate. Basically, after you power it on, make sure you reset the chip, and the hardest thing probably would be adjusting this. So there is a adjust for the gate bias and the reference voltage for the internal circuitry. So I created a little metal plate here, which you can use to basically mount this on the optical table or wherever you're testing. So I created this plate so that you can either mount it horizontally or vertically if you want to change the polarization. So there's one hole where you just mount it and screw it on, leave it a little light, and the other one, if you just loosen it up a little bit, and then you can just slide it in, and then you can tighten both sides, and then you have this end which can hold on to a optical setup, right? And I have a bunch of jumper pins here. Some of them are just for measuring current, so if you ever need to debug it, I'm going to provide you with this little extension cable I created. For example, if you want to measure the bias current, we need to take this jumper out, put this extension in so that it's convenient to attach a multimeter here and measure the current. So this is the example setup I have in the lab here. You can see on your bottom right hand corner the source. I've got 2 Teflon lenses, and I tried to put the imager right here at the focal point, and I tried to keep in the same polarization as the source. And then alright, the connection is pretty simple. Here's this supply connection. Like I said, this is a polarized connector, so this goes to the supply where you have the 3.3 and 1.8, and like as I said, 1.8 you get both the connections in. Make sure both the grounds are shorted, and that's it. Then you switch it on, you see 3.3, and just watch the current. Should be few microamps. 1.8 volt takes about 500 microamps, and 3.3 about 600 microamps. Once you power it on, make sure you reset the part. So that's the reset button. You can reset it multiple times if you want. Source to 10 Hz, and the duty cycle is 1%. Essentially it's a very narrow pulse and a lot of integration time. So clock source on. In order to trigger this clock, you can do two ways. You can either split it right here and take it as a clock in. What I've done here is actually I have a clock out over here. You can take that and trigger it instead, and the output goes to the second channel right here. Say there are 4 configurations here, so right now you can see I've set it to configuration 2, which is basically one of the 4 material designs we have here. PWM clock here, it's a 10 Hz signal here. You can see the pulse width is very small. That's used for resetting it. This is the output. As you can see, at the reset it goes low, immediately goes high, and then after a long time it goes low here. And this can be adjusted using the V-adjust potentiometer. And that's what changes the trip point. You can see that's moving around. And I think anywhere in the middle area, doesn't matter where it is, it's good enough. Now next what I would do is I would zoom into that region so that that's really magnified, and you can see there's a little bit of noise. Actually quite a bit of noise, but fortunately it's all white noise, so we can average it out. So in order to average it out, you hit acquire, and you can see the average is 2 here. The LaCroix is going to have something different, but it'll be pretty similar, so you probably can't see it, but I've changed the averages to about 1024, and then that should quieten the signal. Okay, so this thing is super sensitive to light, so you need to turn all lights off, and even LCD screens, it's really sensitive to light once you open the lid. And you can see now after averaging, the signal is pretty steady. So usually what I do is I turn display, and I turn the persist on, so that way if there is any change you'll know. So I'll turn the persist on here. I'm going to show you the example of just shining light onto the imager, and you should see the persistence tracking. And that's basically this is the trip point of the integrator, and if there is current it will just move around, and you should see the persist mode tracking it. Okay, so I'm going to shine the light right now. Actually it's used to be way more sensitive than this, but I guess the averaging, see, as you can see, the trip point is changing with the integration. Because I'm averaging it 20-40 times, it takes a while. So you have to basically switch on the power and just wait for a long period of time to see if the integration trip point is changing. As you can see, this thing is going up, so essentially it's just moving away, but because you're zoomed in, it shows as this flattening of the curve. I'm going to switch it off like now. So obviously this is pretty exaggerated with the light. I mean, I don't think you'll ever see with your THz signal, but that's essentially what you should be looking for.